Yep, thank you. Hello, everyone. Thank you for attending my talk today. I'm excited to share to you our research on BioSys, an efficient quality control system for manufacturing of sustainable biopolymer-bound soil composites or biopolymer composites. My name is Barney Miao, and I'm a current PhD candidate at Stanford University, and here are some of the other collaborators that helped in this study. Now let's get started. So currently the construction industry I'll bend down. Construction industry accounts for around 11% of global carbon emissions, and the production of concrete single-handedly accounts for 8% of global carbon emissions. So one thing to do to reduce this carbon intensity of the built environment is to develop alternative carbon negative building materials. And in this case, our research group develops something called biopolymer bound soil composites, which uses nature-inspired or nature-based biopolymer waste binders to bind together a granular material into a solid composite for building. You can see here in the micro-CT scan that you have a biopolymer matrix that binds together the aggregates in a matrix form, and you have voids also in the resulting composites. And you also have the SCM image where you see the biopolymer binder basically tightly binding together an aggregate forming your composite. That's one way of thinking about it. The composite is generally 80 to 90% aggregate, also known as soil, any soil, sand, anything you could think about. The soil is not that important. The biopolymer itself and also a solvent. The strength of the material is around 5 to 42 megapascals, and for reference, concrete itself is around 20 megapascals at least, so it is as strong as concrete. But the one main benefit is this material does not use any cement and uses total waste products in its production. So the resulting benefits of using these carbon-rich waste biopolymers is you effectively sequester carbon, hence you will have a carbon-negative building material. So although this sounds extremely attractive and excellent, there is one issue currently not solved by this material family so far, which is the development of quality control methods to help ensure consistency in manufacturing materials. So quality control is very essential for the structural health or eventual building that you create. And some existing structural health or quality control methods include, imagine if you're shopping to wanting to solve this problem, you keep filling your shopping carts, you have like some vision-based methods, some acoustic-based methods, and even some rebound hammer or other type of non-destructive testing methods in material science. And these ones, although if you eventually keep filling up your cart, imagine if you want to cut your grass and I tell you you have to get 5 tools or so, you'll be like, oh no, this seems unnecessarily difficult and not really practical in a large-scale manufacturing scheme. So one thing about BioSys is it's a single-hand system, so you only need one system. And unlike other previous ones, it is uniquely tailored to this material, which has very special, unique development processes that I won't get into too far. It's not a materials conference, but yes. And for BioSys itself, it's a vibration-based quality control system. It's multifunctional. It's efficient, very to use. And BioSys also, unlike many quality control methods, focuses on the initial health or initial fabricated mix design. So if you could track or determine if your initial mix is not appropriate, you could potentially salvage it and prevent waste production or have less waste from manufacture. So for a quick overview of BioSys, I'm going to go a little more deep in each one. So we have 4 pillars supporting the system. The first pillar being your data collection. In this case, you have a BSC sample or a biopolymer bound soil composite, it's abbreviated BSC. And in this case, you check the quality, which involves measuring an impulse and response data. And once you've saved it, you could then, depending on what type of model you want to use, there's 2 models or methods we have developed. A quick model called an XFeet model, which is much simpler, only uses 8 features to train, and also a TS check model, which uses more complex time series classification models to train. So once you choose your model, you can then train your models and finally deploy them for either strength gain or monitoring your development of the material or also the initial health also. So for some type of investigated specimens, I actually brought a specimen with me. It's not a brick. It was hard to bring a brick on a plane across the world. So in order to not bring a brick, I brought a small cylindrical sample so you could come up or come to me later and see what it looks like. In this case, back to this, BSC samples are normally manufactured to a double-sided compaction. So you imagine you have a sample in the middle, you compact one side, flip it, compact it again until you reach this stress level. But for all these samples, we have the same dimensions, but for the control sample, there's no simulate defect, but for the other ones, if you simulate a defect, you can imagine you're embedding a defect or simulating one in the middle. And for the ones we have simulated some high-density defects and low-density defects. Those are typical from mixing issues where you have some clumping of biopolymer, for example. And you also have regions of significant debonding and shrinkage cracking, which is very important and prevalent in material development. So those are we try to capture a wide range of defects in our study, which is very prevalent in any material development. So we have 8 types of defects versus 1 control sample. So for our data collection, so you can see here the BSC sample is mounted on a dynamically isolated platform, so it's separated from the ground. And in this case, for each sample, you would imagine if you put your sensor in the bottom left corner and you tap on the top right corner, you basically would tap this for 5 continuous 10-second time intervals to collect your data. And you would basically repeat this for every sensor and hammer pairings over the specimen. That's how you would collect the data. And you can imagine it's very simple to use. You simply attach your accelerometer and tap. And it's very similar in regard to when you have a medical checkup of a doctor. If they check your heartbeat or anything, they just put a stethoscope and listen in. So that's essentially a very, if for medical people, I don't know if there is, but one of our collaborators is a medical person. So the doctor reference is this. So that is our analogy here. So once you collect the data, you essentially have the hammer impulse as shown on the top with the individual impacts, and you also have the response that you measure for the 10-second time interval. For all of them, they might look very identical, and essentially what we do here is we segment them into individual subsequences based on the individual hammer taps. So you could look at individual responses and zoom in and see the features there. Once you do that, so now how do we solve the problem? For our model selection, for our X-feet model, which is our simple model or quick and dirty approach, in this one we select the first minimum and maximum peak location and amplitudes. So if you select them, you eventually have 8 features you're considering, which can further actually be compressed into 2 dimensions using a TSNE. So this is a very quick approach that takes only a few seconds to train, typically less than 10 seconds. For the TS check model, it's a little more complicated, and in this case, we tried a few time series classification models, and in the end, we used a rocket classifier, which uses up to 20,000 dimension features. It is a little difficult to plot 20,000, so you could imagine there is many peaks and amplitudes and other features we're considering in this model. One other thing or challenge to note is because we are manually applying an impulse on the specimens, there is a variance in terms of the hammer amplitude or impacts per tap. So in order to account for those things, or it'll be pretty bad if you don't, we have for the X-feet model, we would basically filter out or do a filtering approach where we would look at the amplitudes of the force of the impulses. And in this case, we would filter out based on if the impulse is within 10% of the mean force that you measured. You would basically, when you do that, you filter out approximately 80% of the subsequences, which has some issues in terms of potential data imbalances when you train. So that is one issue of this approach, but it's the quick and dirty one. And in our more sophisticated model, that is much better. In this case, we would then just do a scaling approach where for each type of hammer impulse, you would just scale the response one based on the hammer amplitudes. And in this case, you would keep all your subsequences, so you have a lot more data for your training. Now for the deployment of the model in action, BioSys for defect detection for the 9-class accuracy currently around has an accuracy of 70% for the X-feet quick and dirty approach, but for the more sophisticated model, it's around 98%. If it's a very good performance, and if you wanted to look at, if you didn't really care about what type of defect your specimen had, if you just wanted to know Is there an issue with my wet mix? You would basically have a two-class accuracy, so you just change all the previous X's into reds. And you can see here a clear distinguishment between a proper biopolymer composite and one with a simulated defect. In this case, you can see XBeat has an accuracy of up to 80%, and now for the TS check model, you have an accuracy of almost 99, and that is very good performance that we had. Another thing I want to show you, I didn't show the compaction thing for time considerations, but in this case for the strength gain, another benefit of this is for this material, unlike concrete, which undergoes hydration chemical reactions. In this material, when you have your solvent in the wet mix, it basically hardens through an evaporation process called desiccation. Typically in the field, you would measure this through a mass loss basis, so you will weigh your samples, but this is not really convenient for samples that are too large, where you can't weigh them anymore, or if they're in an area where, or if they're in a specific dimension where you can't weigh them also. So in order to solve this issue, the BioSys system can also be used for strength gain monitoring. The image shown here is a computational model showing desiccation, how it occurs, and you can see here a drying front forming or crust forming that shrinks continuously into the material. But how does BioSys perform? Well, in this case, you can see in the figure, the BioSys classification for the XBeat had accuracy around 77%, and for the other one had 100%, and although it's 100%, if you looked at a regression problem, it's not really 100% perfect, so but it's pretty much along the expected theoretical strength gain formulation. And if I wanted to conclude this, or if I wanted to put this whole presentation as a 1-minute speed talk, there are three key takeaways to take away from this presentation, which the first one is that BioSys is a simple quality control tool that could monitor the health of your sample or your sustainable materials. The TS check model, the more complicated one, has a higher accuracy, sometimes up to 99, 98, very high accuracies. But it needs a little more time to compute and probably needs a few minutes instead of a few seconds, so depending on how fast you want your results. And if you just want a rough guess, there's multiple methods you can use. And also, BioSys can quickly, relatively, detect and track the strength gain and defects with relatively high accuracy. So these are three, if you're sleep deprived or anything like that, 3 points to take from the presentation. And how does this all fit in? So how does materials person fit in? Well, one thing about thinking about this is when you want to develop sustainable materials to help transition to a more green built environment, you would obviously want to develop new sustainable materials that are completely independent of fossil fuel industries and are replacements for a lot of conventional materials like concrete or asphalt, or asphalt as Americans say. I'm from Canada, so we pronounce it differently. You could invent your materials, and once you develop the material, oh, well, it's great news, but there's so many other considerations to do. So my research also involves some life cycle assessment, which would help guide the development or design of these materials, along with some microstructure modeling or microstructure analysis, where you look at characterization of the material, along with some modeling considerations. And also, even if you invented a very good carbon negative material, you would still have to consider the end of life use of it. So if you were to simply throw it away in a landfill, that's obviously not a good idea. So one thing that we look into is how you could basically recycle these sustainable biopolymer composites and further reduce waste in that regard. So you could transition towards circular construction. And finally, for how BioSys fits in, well, that fits in the smart manufacture and sensing part of this framework, where you would look at the non-destructive testing and other tools to help manufacture these materials. And this all fits into the framework of smart circular building materials for transitioning towards a cleaner environment, which we all would like to live in. So to finish off, some acknowledgements. So some other co-authors of this work is Dr. Yiwen, who is now a postdoc at Stanford University, Dr. Andreas Theissler from, I'm going to butcher it probably, Allen University of Applied Sciences. Okay, and Andrew C. Lesh, a fellow PhD student in the research group I'm from. Dr. David Loftus, who is a medical scientist researcher at NASA Ames Research Center. And also Dr. Michael Lepech from Stanford University. Also, one last thing is if you wanted during the next coffee break, there's no more, but if you're flying out in the morning and want to drink coffee and read more about our materials, feel free to scan the paper there. It's about the life cycle assessment of the materials and other information. If you have any questions, feel free to email, and also I'm happy to answer questions here. Thank you very much.
Any questions?
Thank you very much. Really interesting. This might be a bit of a stupid question, but I guess with the hammer testing, if this were to go to a more productionalized environment, would that potentially be something that could be, I guess, automated to solve the kind of different strike force?
Yeah, that's not a stupid question. That's an excellent question. There's no stupid questions. So for the hammer impulses, we did the approach of the manual one, and that is a certain challenge that we had to overcome. But if we were to repeat this, or if you were to do this in a large-scale manufacturer, you could technically, as long as you know the load you're imparting onto the specimen or your platform, you don't need to really have the manual tapping. So you could actually have a metal ball, for example, or some type of other known thing, drop it on the specimen, and based on the height, you already know your force, right? So there's also some other automated approaches where you have a constant imparting of load. But for the simplicity of this, we just use a hammer tap for a simple purpose. But there are much better or other approaches that you could take. But it's an excellent question. Thank you very much.
Thank you. And I guess broadly, how far away from, I guess, being used in real construction would you say these kind of materials are?
Yep, that's also an excellent question. So part of the thing doing research for this is there's obviously a potential commercialization of this. So that is something we are thinking about potentially doing a demonstration on site somewhere in Stanford potentially. That is something that is in the works. Probably, well, in terms of the current there's a lot of these materials that we've been doing in the research group at Stanford, and generally for the introduction of new materials, it takes around 10 years or so since its inception. You would have to overcome a lot of building code requirements and other satisfactions you have to do. So that's something we're always working towards, probably in the next few years, hopefully, or 1 or 2 for a small demonstration on campus. But that's an excellent question. It's always something I'm thinking about also. Yeah, thank you.
Thank you. So that's an excellent talk. So let's thank the speaker again.